But if you take the minimum, it may happen still with the probability 1/3, but the other 2/3 are higher. So the minimum is available for sure. Okay? So this is something that you may say, this is very wise, because I take the maximum of what I can rely on for sure. This implies that you may obtain more, of course, if you adopted a less prudent decision. But this is reasonable. I mean, this could be something that you can propose to your customer, your client. And you may say, okay, given that there is uncertainty, I can define several possible outcomes for your benefit, which correspond to several different decisions. Let's take the decision that maximizes the minimum benefit. It's like there are several situations in which you have a range of uncertainty, which means that you are like, if you don't know how much petrol is in a car and you have to start for a travel, and then you don't know, again, the content of the petrol in the car, but you know for sure that at least you make 10 kilometers and maybe up to 100. Okay? And then, of course, you are, for sure you know that you take 10 kilometers. And if you have another car and there is a range that is between 50 and 1,000 kilometers, you may be tempted to take the second car, because if you have to make a long trip, then of course you may think, okay, I save a lot of money because I can make the whole of the trip without putting more petrol in the car. But then you run the risk that the range, my example was not fine because the example should be from, okay, correct, sorry, from 50 to 1,000 is one range, and the other range is, should be, in order to give more safety, let me say, let me write in the blackboard, otherwise. So it's autonomy of a car, the example, okay? And therefore you have car 1 has an autonomy that ranges from, let me say, from 10 kilometers to 1,000. This is car 1. Car 2 has an autonomy that ranges from 50 kilometers to 200. So you may be tempted to take this car, because if you have to make a travel that is like 500 kilometers, this car may allow you to save money. If you take the second car, it has a higher, lower autonomy, but for sure you have to stop to put some more petrol after 200 kilometers. And let's suppose that your first petrol station is at 40 kilometers. So with the second car, you are sure to get to the petrol station on time. With the first car, you are not sure. So if you want to be very prudent, you would take the second car, because at the minimum, you stop at the petrol station, the first one, and you put petrol in the car. With this car, you may complete your travel without putting any petrol, but you may run out of petrol before getting to the petrol station. So are you willing to take a risk or not? If you are willing to take a risk, you may decide, okay, maybe that I take this first car. Of course I take this because I also like the idea of the suspense, etc. But on the other hand, if you want to be very sure, very safe, you would take this one, because you are sure that you at least stop at the petrol station and you move forward. And the criteria of the maximum of the minimum would tell you to take this, because your lose is, again, is not a failure. With this car, you run the risk of failing. You don't get to destination. In this case, the minimum result is achieved. So the maximum of the minimum would be take this, because you get to destination. This is wise. And in the example that I made to you, you just have to compute all the alternatives, and that's fine. So this is the criteria of the maximum of the minimum. But let me say that the criteria of the maximum of the minimum can be too prudential in some cases, because in some cases the maximum of the minimum can lead you to a decision that are really efficient. And there are a lot of examples that I don't want to make because you know, it takes time. But if, for instance, you think at any gambling exercise, gambling is where you bet and in order to try to increase your money. So the maximum of the minimum would suggest you not to bet in any case, because if you don't, any bet is a risk. If you don't want, implies a risk. If you don't want to take any risk, you wouldn't bet. And this is the criteria of the maximum of the minimum. But let's think to a situation in which you have the opportunity to bet on something where you have 90% of probability to win, or let me say 99% probability to win. Like if you have a ball lot where you have to pick up a number from 1 to 100, and a person tells you, if you give me 100 euros and you pick up a number, if you pick up number 1, then I take your 100 euros. If you pick up any other number, I give you back 200 euros. You would bet, of course, because if you are sure that the bet is fair, it's 99% of opportunity to win. So you would bet, everybody would bet. But the maximum of the minimum, even in this case, would suggest you not to bet, because the minimum is 0, you lose your money. So this is an explanation that this is inefficient as a criteria. We need something more than the maximum of the minimum. The maximum of the minimum just says don't take any risk in water resources management, which is not really something that in water resources management you always have to take some risks. So we need a criteria that can quantify our propensity to risk, not in a fashion where no or yes, but we must be allowed to introduce a ranking, a quantification, a gradual quantification of our propensity to risk. And again, we can use utility theory. Again. But in a very, I think, smart and useful way, but we need a different definition of utility, because so far we used utility as a means to convert a performance with respect to a criteria into a number that ranges between 0 and 1, which is the utility. So we used it in this context. First of all, in the context of no uncertainty, we used utility to rescale a performance measure with respect to a criteria, and the performance measure can be also an economical benefit, for instance. Or maybe we used also the decision variables, but as I said, it can be used to convert an economical benefit in the range of 0-1. But we used it in the presence of no uncertainty, in the context of no uncertainty. And I said there are many possible ways to rescale this performance measure, like the economical benefit in the range of 0-1. Now we have uncertainty. So let's refer again to the economical benefit as performance measure. So the problem is still how to convert the net benefit in the range 0-1, but this net benefit now is uncertain. So we need a different definition, a different approach to utility. Utility is defined in the same way it ranges between 0 and 1. With respect to the performance measure is a not decreasing or not increasing function. And if we speak about economical benefit, is not decreasing, but needs to be defined in a different way because you know, it's clear the economical benefit is uncertain. Okay, so let's see how this can be done. And these are the three axioms. Utility is equal to 0 and 1 for the minimum and maximum benefit respectively. These are now formulated in the context of utility of a benefit, and therefore you see them formulated in a slightly different way, and utility is increasing for increasing benefit. Or let me say, here should be corrected, not decreasing for increasing benefit. I will correct it. Now they are online in the present form, but I will correct it. The reason why it is mistaken here is that I realized only in the past couple of years that in the water resources management, the utility function could be also horizontal for increasing net benefit. Because, you know, there are some, as I said, if we reach a certain water allocation, even if we increase the allocation, the benefit and therefore the utility doesn't increase. So this definition is suited for, in the context of utility theory is most used, but in the context of water resources management, we need to basically say that it's a not decreasing function. Okay. Now, we need, before reading here, we need to basically refer to a situation where we have a benefit that can be achieved from a decision. So here on the axis I have the benefit, and usually this benefit ranges from a minimum to a maximum in water resources management. The minimum can be 0, but let me refer to a more general situation where the minimum is given a value that I indicate with MB min x. And also I have a maximum, MB max x. Usually, even in the presence of uncertainty, I can define the minimum and the maximum with a good precision. The minimum can be 0, as I said. And of course, to these values of minimum and maximum, if I put the utility, which is expressed as a function of the net benefit, which in turn depends on x. So utility is 0 for the minimum benefit and is 1 for the maximum benefit. Now the question is, what is the utility for a given benefit MB star? So if I have an intermediate benefit between minimum and maximum, what is the utility? But this benefit is uncertain. So in the previous case, my question was just, let's suppose that you have this benefit for sure. What is the utility? And I said it can be a linear change, a linear variation, or it could be different depending on your situation. Because even money, you know, maybe that after a certain amount of money, the utility increases, the gradient of the utility changes. So in this case, the situation is more complicated because this benefit is uncertain. But if I refer to MB star, I know for sure that this is uncertain, but I know for sure that there is a minimum benefit that in any case I will always take, which can be 0. But let me say that, okay, this is uncertain, but usually I can say that for sure there is a minimum that I can always take. And for sure, there is the maximum, which I cannot pass. Okay, so I have uncertainty means that if I refer to a benefit MB star, I'm not sure of getting it. What I'm sure is that at most I get the maximum of the benefit, at least I get the minimum. Perfect. This fact can provide us a means to define utility of this benefit. And in order to estimate the utility for the benefit MB star for a generic benefit, let me refer to a situation where two events may occur. And let me see if the same thing that I'm going to write. Yes. So, here there is only the difference that I didn't put the star in the indication of a given benefit, but it doesn't matter. So, there is a first situation in which I get the benefit MB star x. Perfect. This is not given for sure, because it's uncertain. So what is the alternative? The alternative to this situation is that we get MB minimum with a probability, let me use the same 1 minus p, and MB max x with the probability p. So uncertainty means that if you refer to MB star, you don't have it for sure. You may have MB star, but you may also have the minimum with a certain probability and the maximum with another probability. And let's suppose that we can identify a probability p such that you get the minimum with probability 1 minus p and the maximum with probability p. Probability, when we talk about discrete event, ranges between 0 and 1. So basically, when we talk about probability of when tossing a coin, probability of head or probability of tail, they are 0.5 and 0.5. And when you have only two possible outcomes, the probability should sum to 1. These are the basic axioms of probability, is implicit in the definition of probability. So if you admit that your uncertainty is given, why? Because you are not sure of getting MB star, and you admit that the alternative is given by these two possible outcomes, only these two possible outcomes. If I don't get MB star, the alternative is that I get the minimum or the maximum, then I can define a probability p corresponding to these two possible outcomes. This is a simplifying assumption. Of course, you may say, but there are many other possible outcomes. Let's suppose that uncertainty can be represented in this way. Okay? Okay, now, if you are asked, would you prefer to get MB star for sure, or would you prefer to get MB max with probability p? If you would be allowed to choose, and the alternative is, if you fail in getting MB max, you get the minimum with probability 1 minus p. So basically, if one would tell you, would you prefer a situation where you get a benefit of 60, or a situation where you have a probability of 10% of getting the benefit of 100, and the probability of 90% of getting a benefit of 10%, of 10. This is similar to the example of the car. So you would, what would you do? You would evaluate the probability, and if the probability of getting the maximum is huge, then you would prefer the second alternative. Conversely, if the probability of getting the maximum is low, you would prefer a benefit for sure. Now, let's define utility as the value of P which makes yourself or the user, which makes the two alternatives equivalent for yourself and the user. Because think of the situation, let me call back again the example. If you are given for sure a benefit of 60 and a benefit of 100 with probability which is equal to close to 0, you would say no, I prefer this solution. But if the probability of getting the maximum increases, you will arrive at a certain point where you are tempted to take the risk. And therefore, of course, you get to a value of the probability which makes you equivalent to alternatives. Okay, let's define this value of the probability as the utility of the benefit. And think to this situation, if you are very unwilling to take a risk, very unwilling, you would prefer very high value of probabilities for getting the maximum. And therefore, it means that you give a high value of utility to the given net benefit. So if I look at this situation here, I may draw a utility curve like this, which means that I start from, I give high value of utilities to lower benefits. Conversely, I may draw a utility curve like this, where I give high value of utility only to high benefits. So my question would be, is this prudent or not? So what does this mean? It means that even for low values or benefit, I give a high utility. What does it mean? It means that even for low values of MB star, I want a high probability of getting the maximum to prefer the second alternative, which means that I am prudent. Conversely, if I give a low utility to low benefits, it means that even for low values of the benefit, I am happy with the second alternative, even for low values of probabilities of getting the maximum. Which means, and even for increasing values of the benefit, still I prefer the maximum, I prefer the chance, the risk, I prefer to bet. And it means that I'm willing to take the risk. It means that for the sake of getting the maximum, I'm willing to bet, to get the risk. So, and these are two alternatives. This is prudent, and this is risky. You still don't know how to use it in taking a decision, but I can tell you that you will see that taking the decision, selecting the decision becomes straightforward once that you understood this concept. This is the key step, which is not so easy to get. But once that you get this step, once that you understand why this utility function is prudent and why this is risky, once that you understood this, then you will see that moving forward is straightforward. And this is what is written here. And look, this utility function is very subjective, because it reflects your propensity to risk. It means that if you have a risky decision in front of you, which can give you a very high benefit potentially, you are willing to take it, even if you risk the failure. So for the case of the car, you would have no doubt, according to this kind of utility reasoning, to take the car that has the probability of the longer autonomy. But this is subjective, so in this case as well, your client may have a different utility function than you, but it becomes easier on the basis of this agreement, on the basis of an example that you can make to him, to reach an agreement. So you can make an example like, would you prefer to get, with a probability of 90%, the opportunity of irrigating your crop until the end of August, or would you prefer to start to dropping part of your crop, like you don't irrigate 10% of it because you want to be sure that the remaining 90% is irrigated till the end of summer for sure. And he may say, what is the probability of getting to the end of August? And you say 90%, and he may say, well, it's fine. And then you reach the agreement. Or he may say, no, I want a probability of 99. Which means that the utility increases for the lower benefit. Now I have an example to show you, which clarifies that moving forward, once that you understood this step is easy, and I propose to try to see this example, because I think it helps in clarifying the situation. Again, I have my benefit function, and the three vectors are given by these values. And this gives rise to the three curves that I already shown to you. I have already shown to you. Again, these are the three vectors. So again, you have only three possible outcomes. So uncertainty is given by the fact that you don't know what is the right one, but you know for sure that one is right. Okay. So I could select the maximum of the minimum, for instance, but let's see what happens. These are the three curves. And so basically, you may decide to get the three optimal allocations for each of the vectors. And therefore, the three optimal allocation, you may prove that are given by these three numbers in the first three rows of this table. So 28 for W1, 38 for W2, 42 for W3. And then you can compute for each of these optimal allocation the three benefits. What I did before, in order to show the graph with the maximum of the minimum. And look, given that 28 is the optimal allocation for W1, you would expect that the other allocations have a lower benefit. In fact, you see that they have a lower benefit. So if you move downwards in the table, this is the optimal allocation for W1, which means that it should be the one that gives the highest benefit. If you change the allocation, you should get lower ones. In fact, they are lower. I will explain to you what is the fourth row. The first three are given by the optimal allocations. And then let's move now to the second optimal allocation, which is the optimum for W2. In this case as well, you see it's the highest. And then the optimal allocation in the third row for W3. And again, you see it's the highest. What is the fourth one? It's an allocation that I picked up by chance. A fourth possibility. So let's suppose that I get an allocation of 30, and then let's see what happens. This is the average benefit, and this is the minimum. So what is the maximum of the minimum? The maximum of the minimum would be this allocation. So if I decided according to the maximum of the minimum, I would take an allocation of 42. One may say I take the maximum of the average. This is a criteria that I didn't tell you. Basically, yes, you can do that. The maximum of the average would lead you to select the last one, 72.26. Okay. And now, what are these benefits? Let's suppose that I consider only these four decisions. These benefits are all the possible outcomes in terms of benefits that I can get. So I can use I can use utility theory now to give a utility to each of them. And let's suppose that after the interviews, after the consultation, you end up with, this slide says that there is, you can take the maximum average or the maximum of the minimum. And let's suppose that you give this utility function to this benefit. And this is, this is a shape that is not really the best one. I just went by chance. But this is not decreasing, so that's fine. This is the benefit, and the minimum is about 61. I think the minimum is the upper one, which is 61 and 18, and the maximum is the last one. So let's suppose that this is the utility. As I said, I just went by chance. I gave 0 to the minimum, I gave 1 to the maximum, and it was a not decreasing function. It is a not decreasing function, so that's fine. Okay? And then I can assign a utility to each one of these benefits. So let me now, let me see. I was hoping, I'm missing a table, just 1 second. Okay, let me now explain at the blackboard. And let me go back to this table here, this one. And this table, I'm copying the table here. I have here the decisions, so they are named 1, 2, 3, 4. 1, 2, 3, 4. And then I have the benefits for W1, W2, and W3. So here I have W1, W2, and W3, okay? And I have these benefits which, let me copy just the first row, 79.22, and the second is 74.97, and the third is 61.80. Perfect. And I have a utility function that allows me to compute the utility for each of these benefits. So I could write U1, U2, and U3. And basically they are, I go in the table that I depicted to you to pick up the utilities of these three. This has a utility of 0. I remember that because this is the minimum. So let me see the utilities of 74, 97, and 79.22. This is 1. And the 74.97 is 0.6. Now I can compute an average utility here. And what is the average? Keep in mind that these three vectors can occur with probability 1/3. They have equal probability of occurrence. So it means that the probability, the utility of 1 has the same probability 1/3 than the utility 0.6. So the average is 1 plus 0.6 divided by 3, which is equal to its 0.533. This is the average utility. So this is the average utility of the first decision. I can make the same computation for the other decisions. It's straightforward, as you see. And then, what is my preferred decision is the decision with the highest average utility. This is how you incorporate your propensity or aversion to risk in your decision. And basically what you will see, if you complete this table, is that this is the decision with the highest utility. I need to include in these slides this completed table, and also I need to make some corrections. So give me some time. At the latest tomorrow, I will update this file in my website. But basically, what's important for me to convey now is that by assigning the utility at each of the benefits, basically I have an alternative to taking the maximum average of the maximum of the minimum, and this alternative allows me, through utility, to incorporate my adversion or propensity to risk. And this is how utility theory can be used to this end. And you will see that basically, you will see that, let me see the table that I have here. This decision is preferred because my utility function tends to give some propensity to take the risk. If you look at this utility as this solution here, it's a solution that gives a value of the maximum benefit that is close to the maximum, and it gives on the other hand, a lower value of the benefit that is quite low. If you look at the second decision, this would be more prudent because the lower value is higher than 61, but the highest value is lower than 79. If you try to change your utility function by giving an higher utility to the low values, you would see that